In this lesson, we're going to briefly discuss waves. This will allow us to have a better understanding of atomic structure later on. Let's begin with some characteristics of waves. Our first characteristic is wavelength. It's exactly what it sounds like, the length of a wave. You can see it labeled in the diagram below. Although it does not have to be from trough to trough as indicated. It could be crest to crest. It could be from this point here to this point here. But all the wavelengths should be the same for a particular wave. We usually measure in units of the meter since it's a length, although we could use nanometers or millimeters, any variation. There is a symbol for wavelength. It's a Greek letter lambda. It's kind of like an upside down Y. Our next characteristic is frequency. This is not something that you can label on a wave. Frequency is the number of waves that pass a given point in a specific period of time, usually 1 second. So we can talk about waves per second or 1/seconds for our units, although a lot of times you'll see hertz used, and that is equivalent to 1/seconds. Our symbol for frequency is the Greek letter nu, which is kind of like a fancy V. So how do frequency and wavelength relate to one another? Well, if you look at these two waves here, you can definitely see a difference in wavelength. And if the box represents a given period of time, you can see that with a shorter wavelength here in B, you get more waves. So that would be a higher frequency. So shorter wavelength means higher frequency, and the longer the wavelength, the lower the frequency. We can also look at the relationship between frequency and wavelength in a graph form. This would yield an inverse relationship. And thinking back to the equation for an inverse relationship, generically, it is y equals k over x, where k is some constant value. Well, instead of k here, we use c for our constant. And c is equal to the speed of light, 3 times 10 to the 8th meters per second. So when we're talking about light, it all travels at the same speed. Next, we're going to talk about the electromagnetic spectrum. It is composed of electromagnetic radiation, and this is energy that travels as a wave through space. Each type of electromagnetic radiation has characteristic wavelengths and frequencies. However, the speed of all electromagnetic radiation is constant. It is, again, the speed of light. Here we have all the different types of electromagnetic radiation that make up the electromagnetic spectrum. Up at the top here you can see we've got shorter wavelength waves. So based on the relationship we just talked about, that would be high frequency waves. Down here at the bottom you can see longer wavelength waves, and then that would be lower frequency waves as well. The part of the electromagnetic spectrum that would be the most useful to us is the visible spectrum. 400 to 700 nanometers. That's the wavelength range. Please know that range. Notice how the violet fits in right next to the ultraviolet radiation, and the red fits in right next to the infrared radiation. So red, infrared, violet, ultraviolet, and then if you remember from art class, Roy G. Biv, that's the colors of the visible spectrum. Please know the spectrum, please know where the visible spectrum fits in, and please know which end is the high frequency end and the low frequency end, and the long wavelength end and the short wavelength end.